Okay, so let's do one where you have to come up with all of this information for a function. Like find where it's increasing, decreasing, local max and local min, concave up, concave down, and inflection points. And before we get into it, let me talk about the big picture. These two things are first derivative stuff. To answer these two questions, what I need to do is basically just come up with one of these number lines for the first derivative. So I'm going to find the first derivative, and then I'm going to find the spots where it's 0 or undefined. I'm going to mark those numbers on a number line, and then that breaks up the number line into intervals, which I need to fill each interval in with a plus or a minus indicating whether the derivative is positive or negative. Wherever there's a plus, the original function is increasing. Wherever there's a minus, it's decreasing. And by looking at the pattern of pluses and minuses, we can identify local maxes and mins. That's parts A and B. That's first derivative stuff. This has nothing, I don't want to say it has nothing to do with the second derivative, but we don't have to even think about the second derivative to answer A and B. C and D, that's second derivative stuff. To answer these questions, I have to do all of the things that I just mentioned for A and B, except I'm doing it to the second derivative. I'm taking the second derivative, I'm finding where it's 0 and undefined, I'm marking those numbers on a number line, and then I'm filling in that number line with pluses and minuses. And those tell me where the function is concave up and down, and it tells me where the inflection points are. Okay, so here we go. This was f of x. The first things we want to do is first derivative stuff. So let's do f prime. I have the product rule, so 2x ln x plus x squared times 1 over x. And I see that this simplifies. Basically, this goes away, and this is now just x to the 1. I can pull an x out of this, and then I'll have 2 ln x plus, and then this whole thing was just x, so when I pull an x out, that's just 1. Okay, so I'm seeing where this is undefined and where it's 0. So let's talk about where it's undefined. Of course, I don't see any division, so I'm not worried about dividing by 0. Natural log does have some domain restrictions. Anytime I'm talking about natural log, x needs to be positive. But this is the type of thing where if I look at the original function, that has the same domain restriction. So when I'm looking for spots where the derivative is undefined, really I'm looking for spots where the derivative is undefined, but the original function would be defined. And I don't see any of those, because or at least not from the natural log. Because if I have a problem with the natural log here, I'm also going to have a problem with the natural log here. So basically, I can disregard any issues coming up with the derivative being undefined because of the natural log. So that shouldn't bother me. What I should do is set the derivative equal to 0. So set the derivative equal to 0, and luckily I have it factored, so I can just set each factor equal to 0. So one possibility is that x would be 0, except then we remember x can't be 0 for other reasons because we're talking about natural logs, and this is not in the domain of the original function. Or the other factor is 0. So we set that equal to 0. Let's solve for x. 2 ln x equals -1, ln x equals -1/2, x equals e to the -1/2. So, right, what just happened? We took the derivative, we checked where it's undefined, we didn't find anything relevant, and then we set it equal to 0, and we found one relevant answer. So let's make my number line. I'm going to mark 0 here just because nothing's happening to the left of 0. This is just not in the domain. So when it comes to filling in pluses and minuses, I'm not even going to worry about this. This doesn't get a plus or a minus or anything. That's just not in the domain of the function. Other than that, I should mark the value of x that I found, e to the -1/2. And yeah, by the way, this is approximately 0.606. And this is where decimals come in. And so let me say a word about like the appropriate use of calculators on the test. You're allowed to have a calculator, but a calculator in general is not justification for your work. I don't want you to just write down an answer and have your justification be because my calculator told me so. Except, and I'm making an exception right now, except in a case like this, where really I'm just using the calculator to compare a number to another number to tell me which one is bigger. Like right now, I marked two numbers on the number line, and I marked 0 over here, and I marked this one over here to the right. And that picture kind of implies that this number is bigger than this number, right? Otherwise, I would have drawn this one to the left of this one. But how do I know this number is bigger than this number? I know that because I used a calculator. Because I used a calculator to tell me that this one's about 0.606, which is a positive number. That's what I regard as an acceptable use of a calculator on a test. Just using it to produce a decimal, and all you're using that for is to tell you whether it's bigger than another number or smaller than that number. Okay, let me move on. This is our number line for f prime. I just have to fill in pluses and minuses, and like I discussed, there's nothing going here, so basically I just need to fill this in with a plus or a minus, and also this in with a plus or a minus. This involves testing points. That's one way to do it, and this is another spot where using a calculator is acceptable. For example, if I want to fill this in with a plus or a minus, I know this is about 0.606, so if I want to pick a number in here, maybe 0.5 is good. And you can use a calculator to do this. Let me, yeah, I'm using a computer, and I get that this is -0.19. All I care about is whether this is a positive number or a negative number, and I trust the calculator or computer to tell me that it's negative. This is an acceptable use of a calculator or a computer. Well, yeah. To test this interval, I'll plug in something bigger, like say 0.7, and this is the same story. Let me just click here. So I get 0.2 something. All I care about is that it's positive. So there we go. I am ready to start answering some questions. Part A, if you recall, was to find where it's increasing and decreasing. It's decreasing here, increasing here. And when I put my answer for increasing, I'm going to put my interval. I'm going to write the exact answer. I'm writing e to the minus 1/2 to infinity. I'm not writing 0.606 to infinity because that would not be exact. E to the minus 1/2 is not exactly this. It's just approximately that. And it's decreasing 0 to e to the minus 1/2. Part B was to find any local max or min values. A local max would be if I saw a plus followed by a minus, which I don't see. I do see a local min. I see a minus followed by a plus. I see a local min at x equals e to the negative 1/2, where f of x, I should say the value of f of x, because if I put that into the original function, I'm going to get e to the minus 1/2 squared natural log of e to the minus 1/2. Okay, this is interesting. Let's talk about how to simplify this. You multiply exponents, so this would be e to the minus 1. I can simplify this using log rules. I can take the negative 1/2 down, and then it's just natural log of e. The natural log of e is 1. Remember, log base anything of itself is 1, and this is log base e of e. So this is 1. So, okay, this is 1 over e, this is negative 1 over 2, and this is not doing anything. So I get negative 1 over 2e. Okay, and that's the value of f of x at the local min. So let's do it all again, because we need to do parts C and D, which is the second derivative stuff. So now we are going to repeat this whole process, but for the second derivative, not the first derivative. Here we go. Oops, and I need more paper. All right, so we had, for our first derivative, it was like this. Our second derivative would be the derivative of that, so 2 ln x plus 1, like times 1, right, because the product rule, plus x times 2 times 1 over x. So this is 2 ln x plus 1 plus, well, actually, plus 2, so this is just like plus 3. Sorry, it's messy. 2 ln x plus 3. Okay, good. So we do the same story. We check where it's undefined. I'm going to say the same thing Yeah, what am I saying? The natural log requires x to be positive, but I'm going to say the same thing about that. Natural log was appearing in the original function as well. So the original function, the domain only includes positive values. In other words, I shouldn't worry about this natural log being undefined because that's just not in the domain of the original function. So we're supposed to check where this is undefined, but I don't find any relevant points in the sense that I don't find any points that are in the domain of the original function. So what I should do is I should set this equal to 0 and solve for x. So I get x equals e to the negative 3/2. And this, I'm sure we're going to want to know a decimal for, so let me just go ahead and do it. That is about 0.223. Okay, so where are we now? Remember, we're just doing, our goal here is to make a number line for the second derivative. I checked where the second derivative was undefined. I didn't find anything relevant. I checked where it was 0, and I just found this. So here's my number line. Again, like I did last time, I'm going to mark 0, and then this is like a no-go zone. We're not going to bother putting any pluses or minuses over here. That's all irrelevant. But I've got 0, and then I've got this point. So I need to put a plus or a minus here, and I need to put a plus or a minus here, and so to put a plus or a minus here, I should plug in something in here. This number is about 0.2. Why don't I plug in 0.1? And I'm plugging it into the second derivative. To fill this in, maybe I'll do f double prime of 0.3. And I am just going to use a computer to do these. Sorry, this will take just a second. So for this one, I get negative 1.6 something. All I care about is that it's a negative number. For this one, I get 0.59 something. All I care about is that it's a positive number. Okay, so then let me draw my conclusion. If you recall, part C, where are the instructions? Part C was to find where it's concave up and where it's concave down. Concave down, concave up. Part D was to find inflection points. An inflection point is anywhere where you see a transition from a minus to a plus or a plus to a minus. We see exactly one of those right here. So the inflection point, I'd like to give the coordinates of the point. The x coordinate is this. The y coordinate is something that I will have to figure out because I haven't done the work for it yet. To get the y coordinate, I'm doing f of e to the negative 3/2. If you remember the original f of x, it was x squared natural log x. So it's this squared natural log this. And I can simplify this the same way I did last time. This is e to the negative 3 times negative 3 halves ln e. Natural log of e is just 1, so this doesn't do anything. So this is, okay, this one puts an e cubed in the bottom, so negative 3 over 2e cubed. And those are the coordinates of the inflection point. So yeah, I think this is a good example to show you, especially because we, for some of our work, it was involving these dirty things like decimals, and I'll call decimals dirty because they're not exact numbers, and in the end I want my answers stated in a very exact way. There's no decimals anywhere in my answer, but we had to, like, during the process of producing the answer, I really had to do a few things where I really just had to compare one number to another number to see which one was bigger, and it's hard to do if the number is e to the minus 3 halves. Who knows whether that's bigger than 0 or what, until you try. Well, I guess e to any power is positive, so maybe that's a bad example, but in general, you need to know which number is bigger, and that's fine to use a calculator to tell you that. But the rest of your answer should be completely justified using calculus, and the answer should be stated exactly in the end. Okay, I better cut this off and make a new video.